this is Happy Potato speaking, and this is not procrastination. This is part 2 of the first section of the Edexcel IGCSE Physics Syllabus called Forces and Motion. If you're not a stationary object and are doing something like sitting in a moving vehicle or some sort, there are still upwards and downwards forces acting on you, but it also has forwards and backwards forces like drag and friction. And it's these forces which allow you to accelerate. So if this is you are sitting in a lovely chair, your arms somewhat crossed. There is an upwards force, downwards force, and we can label these arrows. So this would be the force of weight pulling down over you, that's gravity and your mass. That would be the reaction force pushing upwards on you so you don't sink into the chair. This would be the thrust of the car, that's what you're sitting in at the moment. That would be the drag or the friction, depending on whether you're in a plane or a car. Drag if it's a car, friction more likely if you're a plane. But a car still experiences friction, and an airplane still experiences friction. Car experiences drag and friction, and so on and so forth. You get the point. So basically, when one of these forces is greater than another force, how do you move in that direction? Let's say the thrust is this much, well, greater than this arrow here. So what do you do? How do you move in this situation? Well, you will accelerate in that direction. You will accelerate in the direction of the greater force, because there are unbalanced forces acting on the object. So when an object is going at a constant speed, we have to remember, let's say this is a car, it's going at a constant speed. Yes? It's going at a constant speed. It still has downwards and upwards force acting on it. It still has all of these arrows all over the place, even when it's moving at a constant speed. But since the forward and backward forces are equal, let's say this is x and that's also x, that's a force, the speed is constant. So that doesn't mean that the car is stationary. It doesn't mean that it's moving at 0 meters per second. No, that is just simply not the case. When the forces are balanced on a moving object, it means it has a constant velocity. When an object is decelerating, it means it still has the equal upwards and downwards forces. So if you have a slightly better version of the car from before, it's driving the other direction. Yeah? It still has the upwards and downwards forces, except now it's decelerating. So that means the drag force must be greater than the thrust force. So it's going to accelerate in the direction of the greater force, which is the force of the drag. So it is slowing down, it is decelerating. Hopefully you have never seen or been in a car crash, but if you have ever wondered what the purpose of the big bulky front of the car is, where the engine seems, sort of overwrapped, it's because it's a crumple zone. So when a car crashes, the front of the bonnet changes shape. So this is like the before, and then after a car accident, it looks something like that. There's our window. Basically, the crumple zone makes the impact take a longer time to happen, and so it reduces the... I'll just show you the equation that this works with. Force is equal to change in momentum over time taken. And on skateboards, penguins, or ice, or butterflies in the wild or in the wind, it doesn't really matter. We all know that in a tug of war, it will always go in the direction of the larger force, because that's just how tugs of war work. Okay, so there are different types of forces. So if we take the simplest, most transferable cliched physics example of an airplane, let's draw a little airplane. Windows. That is our little physics airplane. We can find it easier to label the forces acting on it. We have the drag, and we've done this like a couple seconds ago, but we'll do it again anyways. The drag, we have the lift, which is the upward force. We have the weight. I'm gonna casually draw the E first. I hope I spelled weight right. I think that is how you spell weight, okay? And then we have the thrust, which is the force of the engines. Right? The drag is essentially just air resistance. And yeah, now we have the more typical magnetic force of attraction we see in everyday life with fridge magnets. So this is a different type of force here. We have fridge magnets. We all love fridge magnets. Those are the best at the fridge. It is a magnet. Because that's so how you spell magnet. Yes. Yes. There we go. It's more like it. Yes. So we know, because of Mr. Fridge, that the forces of magnetism are much stronger than the force of gravity. Why, you ask? Well, the whole Earth, all of the gravity of the Earth, that force pulling down is defeated by the little force between the magnet and the fridge. This little force between this little fridge and that little magnet. This is fridge. This is magnet. That force between them, this force, is greater than force of gravity. And we also have the force of attraction between opposite charges. So like for example in chemistry you can have NaCl. This is an oppositely charged ion. That would make an ionic compound. Yeah, so all of that electrostatic force. It's really annoying. You're trying to put on a sweater and then it's all like staticky and your hair looks like Frankenstein monster and it's just terrible in the morning. So you also have normal reaction forces, not when you react to your annoying sister but yelling, but like when you physically push out of your room to get some personal space. Another less known reaction is buoyancy or upthrust, which makes things float in water. Okay, so here's a rather important section of the syllabus, vector and scalar quantities. Alright, first of all, before you understand the difference between the two quantities, you need to understand the definition of magnitude and direction. Right, so magnitude equals how big something is. Direction is just direction, the direction which is moving in. So, vector quantities, direction, I'll just put north, south, east, west, dot, 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 etc. So, with vectors, they are made up of magnitude and direction, while our good friends, the scalars, only have doodly 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 do magnitude. Well, I'm gonna have to color those two arrows because I can't leave them inside empty. Okay. So vector quantities have magnitude and direction, while scalars only have magnitude. They don't have the direction implied. For example, temperature, you don't have the, well, the direction implied is now 20 degrees to the left. Like, that would be a completely different measurement. That would be sort of like bearings. Temperature, you can't do that. Speed, in 5 meters per second, that doesn't give you direction. If you had a velocity, that would give you the magnitude and the direction. So, yeah, now that we understand the definitions, for example, shall I give you more examples? Okay, one of the most important vectors you need to know is force. Going back to your annoying sister you want to push out of your room, you can't apply a force to her without her moving in a certain direction. So, you know force is a vector because if you try to push a little sis, right, this is little sis, if you try and push her, not that any of you would actually push your sisters, not that I would, I love my sister. This is someone who has severe violence issues. That's violent person. When they're trying to push their sister, who's sad, they can't push them without direction. You can't push someone nowhere. You can only push them and say there, or there, or there, or there, or there, or you get the idea. You can't move someone, you can't apply a force without a direction because it is a vector quantity. Next, we need to know how to find something's resultant force. So let's say we have a box. How very creative, a box. We have 10 newtons of force acting there and 10 newtons of force acting here. So what is the resultant force? Well, since it's in the same direction, you can simply just add these two together and you'll get 20 newtons. So the answer to this would be 20 newtons would be the resultant force, and it would be moving to the right. You don't always have to write the direction which is moving in, but it's always handy to read the question first to see what they're looking for. So sometimes you may need to say to the right, while in some other cases it'll be not necessary to state. So what if we had 10 newtons here and we had 5 newtons here? Well, you would subtract. So the greater one is 10 newtons, right? So you'd subtract minus 5 newtons to get 5 newtons, and it would move in the direction of the greater force. The greater force is a 10 newtons, so it would move in this direction with a force of 5 newtons. So the resultant force for this question would be 5 newtons also to the right. What if we had it something like this? What if we had 5 newtons here and 15 newtons here? Well, you do the same thing. You do 50 newtons minus 5 newtons gives us 10 newtons, and that would be in the direction of the greater force, which is 15 newtons. So it would be moving 10 newtons to the left. That would be the resultant force in that situation. Now, what would happen? This is getting interesting. What would happen if it was equal forces on each side? So if we have 10 newtons, we say the box moves 10. Okay, this is a box. Let's make this more realistic. Yeah, let's add some shadow lines. You know, try and make it look like 3D. This is in the real world, people. This is a box. Yeah, this box, named box. If we had it move, let's change it. Let's think of it in direction rather than force. Well, this is just an analogy for now. But let's say we moved it 10 meters to the left and then 10 meters to the right. Yeah. If we moved the box 10 meters to the left, to be there. Yes. If we moved it 10 meters back in the other direction, where would it end up? Yep, exactly where it started. So let's say it started here. Yeah. Move it 10 meters to the left, it's there. Now I move it 10 meters to the right, it's exactly back where it started. Hasn't moved at all, although it seems to have grown in size. Don't ask me, I had no idea why that happened. So if we think of it that way, if there's no overall movement, if we move something 10 meters to the left and 10 meters to the right again, there would be no overall force if you have it 10 newtons moving in one direction and another 10 newtons moving in the other direction. So the resultant force on this would be 0 newtons. It's not going anywhere. It's staying still. You have a stationary box. How very, very interesting. Now, just our last one, just to make sure that we really understand what this means and how it works. If you have 30 newtons there, that is a very strange 3. I can't stand to look at that. I'll try that again. 30 newtons and 5 newtons. So that would be, yes, you know how to do this, 35 newtons. Moving on to some more interesting physics. Wait, speaking of blocks, have you ever tried moving your bed around the room? It's not easy if you have a carpet and a heavy oak bed, I'll tell you that. Well, that's partly because there is a force of friction acting in the opposite direction which you're pushing in. So, we have our big, massive oak bed, which I so do not own. Let's try and draw an oak bed. This is a fancy bed, has pillars. Yeah, I have an oak bed. We're trying to push it that direction. And you know what? You know what cheeky friction is doing? Cheeky friction is pushing the bed in the opposite direction. So as you're trying, laboring to get your bed moved out of the, well, let's say farther away from the window because it's cold in the winter and you don't want to get, you know, the wind coming in your face. It's pushing it in the opposite direction. Again, with a common triple example, let's go back to Mr. Airplane. Hello, Mr. Airplane. How's your day today? Have a good day. Did you have any delays? Yes, no, no delays. That's very good. Always running on schedule. That's what we need. It's physics air. Let's draw a lightning bolt because why not? Okay, physics air. It's the aircraft. Okay, so it's moving in this direction. This is the direction of the thrust. We have our aerial friction doing the same thing. This aerial friction can be called drag. And it's moving in the opposite direction of the force being created by the plane's engines, which are so amazing that they're bursting into flames. Okay, that was not a plane crash at all. Looking back at the little boxes with arrows coming out of them, we can see some situations where there are unbalanced forces acting on an object, an unidentified white boxed object, right? So let's say this box has unbalanced forces acting on it. So what happens? How does it move? Well, we know this is going to move 10 newtons to the right. But how does it move 10 newtons to the right? It accelerates. So the object accelerates in the direction of the greater force. Now, a clever chap every person doing physics and every person really ought to hear about is Isaac Newton. He made a very important set of laws which he very humbly named after himself, and one of them came up with a neat equation to explain this. Force equals mass. Wait, am I teaching you the wrong thing? No, this is correct. Times acceleration. Force equals mass times acceleration. Right. So it's easy to see from the equation that 1 Newton is the force needed to give 1 kilogram an acceleration of 1 meters per second squared. So this is in newtons, this is in kilograms, and this is in meters per second squared. For example, if the force needed to accelerate a 10 kilogram mass by 5 meters per second squared would give you 50 newtons of force. The same force would accelerate a 1 kilogram mass by 50 meters per second squared, or a 100 kilogram mass by 0.5 meters per second squared. It's just plugging in the values into the equation and solving. So putting it simply, we can say that it takes more force to accelerate a larger mass, which makes perfect sense. It's not very counterintuitive. I'm sure all of you can make sense of that. Right, let's try a more difficult equation. If a truck has a mass of 2,000 kilograms, and the driving force created by the engine is 3,000 newtons, What is the acceleration caused by this force? Why don't you pause the video right now and give it a go and try and solve it. Okay, you had a go? Great. Alright, so if we plug in the values for the equation, force equals mass times acceleration, you have 2,000 here, you have 3,000 here, you get 3,000 over 2,000, which gives us 1.5 meters per second squared. 2,000 kilograms is a lot of mass. Speaking of mass, in this situation, technically we can't call it weight. Although many people do, including people in physics, so it's okay. But what's the difference between weight and mass? Well, they both measure how heavy something is, right? Well, you would be right to say that. And they do measure how much mass something has, basically, in both situations. It's always how heavy something is. But the key difference is that weight includes the pull of gravity from the Earth, if you're on Earth, or on an asteroid, or wherever in the universe you happen to may be. So if you're on the asteroid, it would be the mass times the pull of gravity from the asteroid. If you're on the moon, it would be the pull of gravity from the moon, so on and so forth. So it's not just how many particles of that element are present. So our pet rabbit, this is our pet rabbit. Oh, look at our pet rabbit. We'll call it Tut Tut. Okay, our pet rabbit Tut Tut has a mass slightly deformed rabbit. We'll just go with it. He has a mass of 5 kilograms. Well, what is its weight? This is its mass. What is its weight? How do you find its weight? Well, the pull of gravity on Tut Tut is about 9.81 newtons per kilogram. But for the purposes of GCSE, you will be fine just using the value of 10. So, how do we get weight from mass? Well, we could write an equation. We could say that weight equals mass times g. G depends on where you are. The mass is 5 kilograms, and we'll use the value of 10. That gives us a weight of 50 newtons. So, poor old Tut Tut may feel ashamed of tipping the scales at a whopping mass of, well, weight of 50 newtons, but there's absolutely no need to worry because it doesn't mean he's heavier. He's still the same mass. It's just when you include the pull of gravity from the Earth on Tut Tut, it's 50 newtons altogether as a weight. A force, in other words. Okay, so a man is in an anti-gravity chamber. A man, these are definitely your typical physics questions, all the way. This is definitely something you're going to see in the paper. Don't take that literally, please. Okay, this is the anti-grav chamber. This is anti-grav chamber. Yes? Normally has a mass of 50 kilograms. This hat normally has a mass of 50 kilograms. 50 kg. Let's get this out of the way. Yes? He's a very light man by American standards. Nowadays, the average mass of an American man is 88 kilograms. Okay, let's be realistic. Let's follow the data. Normally has an average mass of 88 kilograms. So let's just make this a little bit more. There we go. A little bit more realistic to the times, shall we? 88 kilograms. Right? Alright, okay, let's make this more realistic, okay? Plus the 3 kilogram weight of his hot dog and his soda. That's more American. Alright, so he sets the gravity in the chamber to 60% of the gravity on Earth. So what's his weight? So if we do 60% of 10, which is the value of gravity on Earth, we get 6. So the pull of gravity in the chamber is set to 6 newtons per kilogram. And if his total mass, including his food and drinks for the evening, is 91 kilograms, then he would have a weight of 6 times 91, which equals 546 newtons, I believe. Okay, so Fat Man over here steps out of the anti-grav chamber, right? He steps out of the chamber. Here he is. Stepping out of anti-grav chamber. But he forgets that the gravity outside the chamber is stronger than the gravity inside the chamber. So his hot dog drops to the ground. Rolled hot dog. Let's draw a nice hot dog. Hot dog. There we go. Is that it? That's a horrible hot dog. Let's try again. Yes. 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 I tried. No, that's a hot dog. Okay, we'll go with this as our hot dog. So it drops to the ground. Since he was just letting it float around in the anti-gravity chamber, what are the forces acting on the falling hot dog? Well, we have the weight, which is basically just the pull of gravity, and in the opposite direction we have the air resistance or drag. And remember the boxes with arrows coming out of them? Remember those? Well, this is basically the same thing, except now the forces are vertical. Well, we know that the force of gravity in the hot dog is going to be stronger than the force of air resistance. Or let's assume in this situation that that is the case. So we can say that there are unbalanced forces acting on the hot dog. And how is the hot dog moving down? Well, there are unbalanced forces acting on the hot dog, so it's accelerating. It's accelerating towards the ground. It's getting faster because remember, with unbalanced forces, it always accelerates in the direction of the larger force. Now, let's say the hot dog was falling a large distance. Let's say he stepped off. Let's say that the anti-gravity chamber was on a cliff, and the hot dog is falling down this cliff. Yeah, it's falling down the cliff. So let's say how would the hot dog fall? Well, the forces acting on the hot dog would balance, because as the hot dog travels faster and faster, there's more and more air resistance. So there's more and more air resistance as the hot dog is falling. And eventually this force, the air resistance, is equal to the force of the weight. What happens then? Doesn't mean the hot dog is stationary. Doesn't mean it just stops falling and you just have a floating hot dog in midair. That would be weird. Not weird. Let's not offend the hot dog. That would be odd. Very odd indeed. In physics terms and in just general. Okay, let's not talk about floating hot dogs. So it's not stationary in midair. It is actually moving at a constant velocity. So this constant velocity achieved because of the increasing air resistance on the hot dog, because as it moves faster and faster there's more air resistance. That sort of balancing of forces, that sort of constant velocity is called terminal velocity. AO, the age-old example of a parachute from the plane. Yay! Now, instead of dropping parachutes from a given height, why don't we just throw this guy named Tim? Here's Tim. We are going to throw Tim, poor old Tim, didn't know what he signed up for, out of a plane. Physics error. Gonna drop him out of there with different sized parachutes. So in the first situation, Tim is just ahead, by the way. So the first situation is gonna have a parachute with a surface area of A. Let's say he's being dropped at 5,000 feet above sea level. So let's say the first time it's the surface area of A. We measure the time that it takes. Let's say it takes X amount of time. So A is the surface area time meters squared times seconds. This is our chart. So let's say the second time we do it, Tim has parachute has a surface area of 2A. So let's say it's just double the surface area. And we get Y for the amount of time that it takes for him to fall 5,000 feet. So if we plot a graph of this data and we did the same thing over and over again with, let's say, 3A, 4A, 5A, 6A, all the way as far as we could until Tim eventually is just too terrified to keep going. If we just do that, then if we plot the graph, we would see, although we probably already knew, that as the surface area, the parachute increases, the time takes for the fall increases also. So as the surface area increases, the time would increase also. So possibly would look something like that. And that's how you'd make an example of this, and that illustrates a general idea. But for example purposes, I would use the following one in a question. Don't bring up the 2A surface areas and X's and Y's. Just use this example. So if you get 5 different sizes of sycamore seeds, especially if you're doing IGC, you need to know about these little guys. They're basically seeds that have these like little flappy thingies that make them fall in interesting ways to the ground. And let's say if we get 5 different sizes of sycamore seeds, something like that, etc. It sort of looked like that thing in Harry Potter, the golden snitch. That's what I'm thinking of. Yeah, sort of a bit. Moving on. Let's stay focused. Yeah. So if we get 5 different sizes of sycamore seeds and roughly measure and label them with their surface area by multiplying the length by width, we could hold one at the top of a meter ruler. This is a meter ruler. Hold one at the top. Yeah. And then we could drop it and then measure the time it takes for it to reach the ground. And then we could repeat this 3 times for each of the 5 seeds and plot a scatter graph with the surface area on the y-axis, let's say in millimeters per centimeter, and the time on the x-axis. The line of best fit would be a diagonal line pointing away from 0. So it would be something like that, which represents a positive correlation leading to the conclusion that the larger the surface area, the longer it takes to fall, which again, you probably already knew, especially after Tim. Okay, so because the larger seeds had more surface area to experience air resistance, this would be your explanation. Essentially, friction with the air that opposes gravity, there is a slowing down in the time taken for gravity to bring them to the ground. Now, stopping distances. Have you ever driven? Well, I say driven, but most of you are not of an age to drive. including me. Anyways, have you ever driven on a wet or icy road and then had the car slide around? Yeah, I know it's scary. I've had the experience with mud on hills with my uncle speeding up a hill in the rain, but we can talk about that later. What are the factors that make this happen? Well, there's a lot of friction between the tires and the road. So we have tires, road, car. Yeah. What are the factors that make the sliding possible? Well, we can list a couple. We can list, for example, first we'll explain the situations where this happens. So when there's not a lot of friction between the tires and the road, let's say with mud, ice, snow, or water, they all act as either a lubricant, here, or let's say as a surface. The ice would just be the surface. Well, actually, with ice, when you have the car driving over it, would melt the ice and make water. And if not, then it would just be slip. It would be slippery because of water. So in each of these situations, it would be a lubricant. And essentially, that means there would be less grip. Well, what if so that's one of these situations. Be the road. Ice, snow, water. Then we'd have the quality of the tires. When tires get worn out, they lose their grip. So when you have a tire that looks something like this, or something of the sort, then this tire would have high grip, because a lot of places where it can hold onto the road, if you will, with its sort of like claws. This would have more grip than this tire. So this tire is grip tire. So it would be, well, the quality of the tires. Quality of tires. And then you also have, what else? Well, you have the road, the conditions on road, conditions. You also have the road itself. If the road is worn out, then it'll have a smoother surface and there'll be less grip. So you can have road quality, I guess, as well. Have you ever been in a car with your parents and you see the light turn green but they don't move because they didn't see the light change, and you're just sitting there like, come on, the light's changed, let's get moving, come on. Well, what are the factors that affect reaction speed? We have age, we have intoxication, we have illnesses, we have how tired you are, tiredness. And there's some studies that show that personality affects this as well. But whatever you do, I would not write this in an exam. Do not write. Okay. Yeah, so these factors basically affect the total distance traveled by the car before it stops, which is the distance the car has traveled and the time it takes for the person to press the brakes, plus the distance traveled by the car before it stops. So let's say this is the distance the car travels. Say it's 5 meters. For the person to, like, let's say, notice someone's in the road and then press the brakes, that would be the thinking distance. And the rest of this, let's say it's 15 meters. This would be the time from, this is brakes, this is brake point. This 15 meters would be the time it takes from when the brakes are applied from when the car stops. That would be the braking distance. Or we can say stopping distance. When you add the thinking distance plus stopping distance, what does that give you? It gives us the total distance traveled by the car before stopping. It's a bit long, but as long as you understand what it makes, you don't need to memorize it in these exact words. As long as you understand what it means, you're good. Fair enough. Momentum. So what the heck is momentum? Momentum is how much an object wants to keep moving in that direction. So the fat American guy has a high momentum towards the food? Not exactly. Is there momentum between this hammer? That is the hammer for now. Happy with this hammer and this nail? Well, if you swing the hammer first, and it's moving like that, well, yes. There. So what if we had a bigger hammer? Let's say mega hammer over here. Have a higher momentum than a smaller hammer. Well, why is that the case? Well, the bigger the mass of the object and the faster it's moving, the more momentum it has. So let's say a train has more momentum than a bicycle. Yes? Yes. What's an eloquent equation that basically sums this up so it's easy to remember? Momentum equals mass times velocity. So if we had a change of momentum of 100 kilograms per meters, well, 100 kilogram meters per meter second, and it took 5 seconds. What would the force be? It would be 100 divided by 5, which gives us 20 newtons. And if you're having trouble following that, we can plug it into the equation. We can have momentum equals mass times velocity the momentum is 100 kilogram meters per second. The mass is, the mass is x, and it took, I actually lost my place. I'm not sure what I'm doing. Okay, so let's do some momentum questions. If a watermelon has a mass of 2 kilograms, is shot from a gun at 100 meters per second squared, work out its momentum. Well, momentum, meters per second. Yeah, that will make more sense. So instead of meters per second squared, let's make this meters per second. Yeah, that makes much more sense. Because we have momentum equals mass times velocity. So if we do 2 kilograms times 10 meters per second, we get 20 kilogram meters per second, which is our unit for momentum. Yes, no, maybe? Pause the video and try out this question to see whether it makes sense. A bullet with a mass of 0.03 kilograms leaves a gun at 1000 meters per second. If the gun's mass is 1.5 kilograms, what is the velocity on the recoil on the gun? So the momentum of the bullet equals the mass 0.03 times 1000 meters per second, which gives us 30 kilogram meters per second. That's for the bullet. So if we rearrange the equation, momentum equals mass times velocity. Rearrange this to get velocity alone on one side. We get momentum over mass equals velocity. So the momentum we have as 30, because we just calculated that there, divided by the mass, which is 1.5 kilograms, and 30 divided by 1.5 gives us 20 meters per second. So that is the velocity of the recoil of the gun. Back to the Isaac Newton guy. I don't know why he put it here. They put it there rather, but in the syllabus they put it in now. So it says right now we need to talk about the third law. I don't know why they just put it in the third law, not the second and the first, but we'll just do that now. So third law, every force has an equal and opposite reaction force, right? Well, that's what a lot of people would think, and a lot of people would be right, except there's a little flaw with this version of thinking of third law. Okay, a couple of you are probably thinking, hang on a second. We have an object and it has an equal and opposite. Every force, let's say we apply 10 newtons on this, so it moves to the right? If it had an equal and opposite force, wouldn't that just be the box with the equal arrows outside of it? Wouldn't that just mean it has a resultant force of 0? And would that mean nothing in the universe would ever move ever? You are absolutely 100% correct. That would be the case. So what is wrong with the definition of our third law? Well, first we need to make a more accurate version, a more accurate definition of third law. Let's have object A and object B. So we can say that for every force from object A to object B, for every force from object A to object B, there is an equal and opposite force from object B to object A. So this can also be illustrated as FAB, that's this force here, is equal to minus FBA. And what is this basically saying? Well, it's talking about the fact that it's acting on different objects. So, just in case you didn't get this before, when an object A exerts a force on object B exerts an equal and opposite force on object A. That's a more concise way to say it. This just clarifies that the force is acting on different objects and is exerted by different objects. So, if the force on object B is coming from object A, then the force from object A is coming from object B. Okay, so let's just put object A on one side of a seesaw, A, and B on the other. Let's say these are like actual objects. That one's more sphere-like, and this one's, I don't know what that is, but it's a thing. And then this is our seesaw. So object A is 5 meters away. Let's say this is 5 meters from the pivot, and object A weighs 5 kilograms. Actually, let's make this more accurate, and I'll explain why this is more accurate in a bit. 5 kilograms. So, what is the moment? Okay, not as in the moment when I saw her eyes, or the moment I saw that hot dog if you're the fat American. It's something to do with the physics-related definition. So moment is equivalent to the force, the mass times the pull of gravity from Earth, if you remember. The force, so this actually should have been kilograms. I've made a mistake. This should be in newtons. So how would we change 5 kilograms to newtons? We would multiply this by 10, because that's a gravity on Earth, so equal 50 newtons. Good spot. Make sure it's in newtons, yeah. So that is 5 newtons. So what is the moment? The moment is equivalent to the force, the mass times the pull of gravity from Earth, times the perpendicular distance from the pivot, which basically means the moment is the distance from this triangle bit to there, multiplied by the force pulling downwards on object A. So the answer here would be well, 250 Newton meters. That would be the moment on the left side of the seesaw. Or you could say the anti-clockwise movement. Since if you think of a clock, it goes this way. And this moment is acting in the opposite direction. So this would be the anti-clockwise moment. Okay, it's all nice and crystal clear. And no matter, here's why it was more accurate to draw the weight here rather than there. Why? Well, because the weight of an object, the force of gravity on an object, always acts from the center of the object's mass. And you can always find the center of an object's mass by, if it's an odd shape, by drawing a line which is basically symmetrical and then drawing another line across that. Or, if you really want to pinpoint the center and it's like a really irregular shape, you could hang it from a point and then draw the line there, and then hang it from a different point, let's say there, and then draw the line straight down there, and then this intersection here will be the center of mass for that object. Okay. So what if we had some wonky thing where the triangle bit of the equation is not in the middle? Let's say we had something like this, where the triangle is there, and this distance is 4 meters. Let's say this object here, object bob, is equal to W, and object not Bob has a force 24 newtons, and let's say that this distance, this small distance here, is 0.8 meters. So how would we find W? How would we find Bob? Well, we need to know the principle of moments, which basically says the anti-clockwise moment is equivalent to the clockwise moment, or the sum of the anti-clockwise moments is equivalent to the sum of the clockwise moments. So how do we go about solving this? Well, first you'd solve what the anti-clockwise moment is, and following the equation, that moment equals, in shorthand now, force times distance. We would do 24 newtons times 0.8 meters, which would give us a nice number of 19.2 Newton meters. If we plug that value into the equation along with the distance from the pivot on the right side of the seesaw, we get, well, moment equals force times distance. We get 19.2 Newton meters equals, the force is x since you don't know what it is, and this is just another way of writing multiplication, just a dot, just because if you have the letter x it can get a bit confusing. So x times the distance, which is 4 meters on the other side. So x would just be 19.2 divided by 4, which I believe, wait, have I done something wrong? Yes. Let me get the calculator. Well, I haven't done something wrong. I can't do that divided in my head. That would give us 4.8 newtons. Perfect. Oh, and another thing you need to know, if you have a plank or a bridge which is supported by 2 pivots, and it looks something like this, and you have one there and one there, this force, let's say it's 200 newtons, would, if that's 200 newtons, then what would the upwards force here be? Well, these upward forces would have to be equal to this downwards force. So since we have 2, let's say it's an equal distance as well. It has to be an equal distance actually. So it's an equal distance from this side and an equal distance from this side. Well, it doesn't have to. But for this example, it's going to be an equal distance from each side. This is our object. Then it's going to be equal masses on each side as well. It just makes life easier. So this would have to be 100 newtons and this would have to be 100 newtons. Which will be useful when you're doing more difficult moment questions. By the way, if you ever don't recognize anything in these videos and you're using them for revision, go through your notes or your textbook and just make sure you have a clear understanding of everything you need to know for the exam. Okay, hook a slinky onto your door handle, dangle it over the railings, hang outside the window, all those things we all did in our childhoods. What do we remember? The slinky extends, it gets longer. What do we not so much like remembering? When one of our annoying friends decided they were going to run with the slinky as fast as they could. And what do we hate about this? Well, it stops being a slinky and it just sort of a springy bit, and a whole lot of no. So, what do we call this annoying moment in physics? Well, in this annoying moment in physics, we'd say that the spring has reached its elastic limit. This is the point where the spring stops displaying elastic behavior, and on a graph, if we, well, let's not skip to the graph now. Let's go through everything nice and slow. You could just mess around with the slinky, but at IGCSE, they want you to plot a graph while you do this. Yes, and let's be honest, messing around with the slinky for a while is far from a chore. How would we go about doing that sort of an experiment? Well, there are a number of ways we could do this, but we could just attach a slinky to a Newton meter. A nice fancy Newton meter. It just looks a bit like that, I hope. Which basically measures the mass and then automatically multiplies it by the force of gravity for you. And measure the length of the slinky. Then add some weights, let's say 5 grams worth of weights. Then measure the new length. And then do it again. And again. Until, well, it'll be off the page, wouldn't it? It'll be off the whiteboard, rather. Something like that. And then you could use this data to calculate the extension, which is basically just how long the spring is stretched. And then you could plot a graph of the extension against the force. So you could be like, this is the extension. Force. So as the force increases, the extension increases, yes? But what happens at this point? Well, when it stops extending, it doesn't extend as much anymore, and it stops springing back, here when it starts to bend, we say that this on the graph is what you call the elastic limit. And that's just how you'd show it, by plotting a graph. In real life, you'd see it when it stops springing back. So that's where the gradient changes most significantly. Yay, I have to be honest with you, this is one of the sections of physics that really sparked my love for the subject. At first, it is astronomy. To me, the most interesting part of physics. Yay. Well, the most eye-catching at least. Okay, moving on. In the IGCSE syllabus, there's very little content you need to know for this part of the section in comparison with some of the other ones. So I am sure you already know the gravity is expressed with the letter G, and it has a value of approximately 9 newtons per kilogram on Earth. Now the moon, of course, well, the moon has a smaller mass than the Earth, so it's going to have a smaller pull of gravity. That's why in videos of moonwalks, they always seem like they're floating, or they have huge leaps before they land back onto the lunar surface. So the gravity on the moon is something like 1.6 newtons per kilogram. And on Mars, which is slightly smaller than Earth but is bigger than the moon, it's something like 3.7 newtons per kilogram. So gravity is responsible for a lot of things in the universe. It's responsible for the fat man being fat. It's responsible for the Titanic sinking. It's responsible for pretty much everything, you know, like the rain falling, you know. Yeah. But mainly, gravity is also responsible for orbiting. Literally, the whole universe is filled with things orbiting other things. Think about it. The moon orbits the Earth. This is our Earth, which is spinning on its axis just to make things more interesting. And what else? What else can we think of? Well, the Earth orbits the sun, and this is by no means by scale, otherwise we'd all be so horribly roasted, and the moon would be almost the same size as the Earth. So this is not to scale. So the Earth is orbiting the sun, right? And we are in this thing called the solar system, so there's other planets as well. So that's supposed to be Mars, but it's bigger than Earth, so you know this is definitely not to scale, and etc. All the other planets, which I can't be bothered to draw right now. And then the solar system is going around this thing called the galaxy, which looks a bit like this. Let's say it's an artist impression of the galaxy. And we're like, let's say we're somewhere near the edges. So all of this is floating around in one of these, somewhere in that circle, right? And we're not even near the center of the universe, of the galaxy. We're not, you know, anything special. We're just another little speck on the side. And here's where it starts getting mind-blowing. Okay, let's zoom back in first. Let's go down to the smaller scale before we go to the mind-blowing, right? Okay, so comets and asteroids also orbit the sun. And so we can draw their paths. Just look a bit different. There's a tail. Now, question that has nothing to do with the anything you really need to know for this part of the section. But which way does a tail go? Towards or away from the asteroid / comet? Well, it would go. In fact, why don't you tell me, where does the tail go? Does it go behind the comet, or does it go in front of the comet? You let me know when you get the answer. Okay. Yeah, so the solar system is orbiting the galaxy, and the galaxy is, well, is the galaxy orbiting anything? Technically, no, because, well, all the galaxies, these are all the galaxies in the universe, they're all moving farther away from each other. And the scary thing is it's doing it faster and faster. It doesn't mean that our universe is at the center, our galaxy rather, is at the center of the universe. It just means that the universe is expanding. Why is it expanding? Well, we think it's because of this thing called the Big Bang, which a lot of people think is what the beginning of the universe is. So a big explosion started as a tiny dot with infinitely dense mass and heat, and it just kept getting bigger and bigger and bigger and bigger, and it's still getting bigger today. Oh, so what are some of the uses of gravity? Well, it allows all of those nifty, artificial satellites. It always keeps those in orbit, which is always good. And it also helps those artificial satellites fix our position in the GPS, or global positioning system. Now, about the orbits of these objects. The moon orbits the Earth the same way the Earth orbits the sun. So what I mean is they have a slightly elliptical orbit. So it's not a perfect sphere, but it's sort of like a circle. It looks similar to a circle. So this is like the Earth and moon orbits. And then we have, well, it's because beauty comes, hashtag beauty, B-A-U-T, comes in all shapes and sizes. Not just perfect circles. Okay, sorry, that just had to happen. Okay, so what about things like comets, which can come close to Earth, let's say, or the sun. Let's have this be the sun for a short period, and then shoot off in this direction for a long period of time. Something like this. And of course, this example has an asteroid / comet which is bigger than the sun, which is exactly what we need. So this is what we call a more elliptical orbit. Well, they're both elliptical, but this one is obviously visually more elliptical than the lunar and the moon's, the Earth's orbit. Yeah, and a famous example of this comet is Halley's Comet, which I'm sure you know, which is actually written like this. So I think it should say Halley's Comet, but everyone does Halley, so we'll just go with Halley's Comet, which is an orbital period of about 75 years. So it comes close for a short while and shoots off for a long time before coming back again. Now, we need a bit of math to fix these concepts into place. Well, actually just speed equals distance over time, except with the equation for the circumference of a circle inside. So if you want to find orbital speed or orbital distance, if you want to find the length of this line here, all I have to do is plug in orbital, the word orbital, to this equation. Don't let it scare you. It's just speed equals distance over time. And then here it's just orbital. Again, time period. So the only difference is you're doing pi r, 2 pi r over, and this was what we'd call the orbital distance. A lot of people just see that and get scared. It's just the distance over the time. Speed equals distance over time. So just the equation for that would be orbital speed, if you want it written out, orbital speed equals 2 pi r over time taken, or orbital time period. And 2 pi r again is just the area, the equation for the circumference of a circle. Lastly, we need to know the relative sizes of things. We are on a planet called Earth, which is orbiting a planet in the solar system. And the solar system is in the Milky Way galaxy. Do you remember this? We literally did it like 3 seconds ago. Somewhere there. And the Milky Way galaxy is not the only galaxy, surprise, surprise. It is one of billions of galaxies. And our sun is not the only sun, or the sun isn't the only star, because the sun is a star, in the galaxies, or in the galaxy. There are billions of stars, not because the Milky, you understand this. To put this into perspective, basically, just to get you the numbers and size working right, the number of the stars is greater than all the grains of sand on all the beaches of the earth. So, yeah. And with that profoundly life-nullifying tone, we shall end. Well, last week I said that if anyone wanted me to cover a new topic, I would learn how to solve a Rubik's Cube. I had a few comments from several girls in the year below asking for videos in biology and chemistry and as well. So, yeah, I would imagine that series would start at the end of this one. And here I go.